complete this chapter, chapter 7, and no, I mean chapter 8. All right. So last time we talked about momentum in electromagnetic field, and we said we know the force in electromagnetic field is given by F equals to the divergence of the stress tensor integrated over the volume minus 1 over so it's the integral of the divergence of the Maxwell stress tensor d tau minus 1 over c squared and d by dt of the integral of the Poynting vector over the volume d tau, over the volume. So that's how we determine electromagnetic force, and starting from that and using the definition of the net external force on a given object from what you know in classical mechanics, F is equals to what? Change in momentum, mechanical momentum with respect to time. Using that definition for force, we showed that from here, this electrostatic force, electromagnetic force, can be expressed as dp me by dt is equals to the integral of the divergence of the Maxwell stress tensor d tau, and just by comparing with what we have on this side, we said 1 over c squared, the integral of the Poynting vector over the volume must be the electromagnetic momentum. So we say this is minus dp electromagnetic over dp by dt. And from this we found out that if you add the change in mechanical momentum and change in electromagnetic momentum, that must be equals to this integral. So we say d by dt of p mechanical plus d p electromagnetic by dt is equals to the integral of the divergence of the Maxwell stress tensor d tau. And by defining the electromagnetic momentum density, we were able to find that if rho me represents the mechanical momentum density, if this is the mechanical momentum density, and if rho em represents the electromagnetic momentum density, then using that we showed that rho me plus rho em is equal to what? We showed this one is going to be equal to the divergence of the Maxwell stress tensor. So that's what we discussed last time, and today we will see how to find electromagnetic momentum. We will do an example, and also we will talk about angular momentum of the electromagnetic fields. So let's consider this example. In this example, you are given a long axial cable of length L, consists of an inner conductor radius A and an outer conductor radius B. It's connected to a battery at one end and a resistor at the other. So the inner conductor carries a uniform charge per unit length lambda and a steady current I to the right, and the outer conductor has the opposite charge and current. What is the electromagnetic momentum stored in the fields? So this is basically what the problem represents. So you have these two cylinders, one inner radius A, the outer one has inner radius B, and each of these cylinders carries a uniformly distributed charge. The inner one carries a positive charge and the outer one carries a negative charge. And it's connected to a battery, so and also to a resistor. Then because of the battery there is a flow of current, and because of that current you would have a magnetic field, and because of the charges that are residing on the surface you would have an electric field. So electric field, magnetic field, then you would expect momentum from this relation for electromagnetic field. So if I draw the two-dimensional view of this, let's say, for this example, 33. So let's say this is X, Y, and Z is going to be towards U. So we have two cylinders. One has inner radius A. So this has inner radius A. And the other one has outer radius B. I mean, the other one has inner radius B. So this has radius B. So this one, the inner one carries a positive charge. So let's say we have uniformly distributed positive charge here. And the charge density of that is per unit length is lambda. And the outer one carries a negative charge. So here we have a negative charge. And the charge density here you can take is minus lambda. And also it says, since these are conductors and the conductor is connected to a power source. So if I go here, conductor R. So that's the situation we have in the question, is to find the electromagnetic momentum stored in the fields. So to find that, we must evaluate to find PEM. We need to evaluate that PEM, according to what we have in here, is given by 1 over c squared of the integral of the Poynting vector over the volume wherever you have the field. So where do we have, how do we determine the Poynting vector S? That is given by